We work for the money. Okay. Our next speaker is Mahesh Anand, who's going to talk about reconciling the hydrogen and chlorine isotopic signatures of the moon.
Okay, good morning, everyone. The title may look a bit too dense, and I wasn't sure what the audience here would be like. So this morning I revised my talk, and I hope that you would allow me a bit of digression, because today is a very special day, of course. And let me also point out that two things happened 50 years ago, and literally 50 years ago, because it was 1 hour ago that actually the Apollo 11 crew arrived back here on Earth. And 50 years ago, as of yesterday, was the first royal charter was granted for our university, which is the Open University. So from my point of view, these are two unique events that have actually touched probably over 1 billion lives, right? And I can't be any more proud to be working at an institution and on the Apollo samples. So, and none of this work would have been possible without the superstars that are in our team, like the PhD students and postdocs. And just to mention a few names, Roma Tartes, Jessica Barnes, and Alice Stefan. I mean, the next generation of lunar scientists. What a privilege it has been to be associated with them. And much of the work I'm going to present today has been done by my postdoc, Alice Stefan. And if I can digress for 2 slides today, is about something that I didn't know up until a few months ago, when a colleague of mine from Scotland's OU office said, "Did you know Neil Armstrong had a Scottish connection?" I said, "No, I didn't. Let me do some research." And when I did my research and then ended up writing this editorial in the Scotland's national newspaper, The Scotsman, what I found, more I read about Neil Armstrong actually, more I realized that somehow he was destined to be the first person to be on the moon. And to sum the whole thing up, it seemed that Neil Armstrong had a connection to the Armstrong Clan that actually lived on the border between Scotland and England around 400, 500 years ago. And they were in between the two fighting armies, and they had to take sides whenever it was, the kind of more opportunistic to them, that they would have a flag that on one side would have a Scottish flag, on the other side the English flag. So depending upon the situation, actually, they go by it. And it was just amazing to read about that and to see that actually somebody, 500 years ago, they didn't know that one of their clansmen would be the person walking on the moon. So if they can do it, I think everybody can do it. And to me, it's like a very inspiring story. And just a plug for something I know there has been some amazing TV programs and movies that have been made, and we made a small contribution. So I worked with the BBC and PBS to work on this drama documentary, which I believe will be released in the US very, very soon, but I don't know the broadcast date, but it was premiered in the UK 2 weeks ago on 10th of July. So if you get a chance, please also watch this, among other things. Now, let's get back to a bit of science. So what I wanted to share with you is the latest research that we have been doing at the Open University on the Apollo samples from all the missions. And the topic that today I want to discuss with you is our research on lunar volatiles, in particular hydrogen and chlorine. And this is still an unresolved issue, because we still don't fully understand how we can reconcile what we see in terms of hydrogen and what we see in terms of chlorine. So I hope that I can give you a little bit of flavor of where we are at the moment, but by no means this is the end of the story. In fact, it is just the beginning. And also, I was literally over the moon this week, because we had 3 research papers that were accepted for publication this week, just this week. Yeah? And one is on the very precise age dating of Apollo 17 basalts that Jack would be interested in hearing about later. I'll share with you, Jack. And the other 2 were about our volatiles work. So as of now, we think that the lunar mantle has anything between 1 ppm and 100 ppm water. Now, that seems like a large range, but I think that's where we have come in the last 10 or so years, where we thought originally that the moon had less than 1 parts per billion water. Now we think it's something between 1 and 100 ppm. In terms of hydrogen isotopic composition, we think that the average deuterium to hydrogen ratio in the lunar mantle is between -200 and +200, broadly chondritic, broadly similar to what we see in terms of water on Earth. And it has important implications in terms of where the water on in the Earth-Moon system has come from, and even more broadly in the inner solar system. All of this work in the last 10 years mainly has come on whole rocks, volcanic glasses, Melty inclusions in those volcanic glasses, and the mineral apatite, plus some nominally anhydrous minerals. The majority of the water-related work has been done on mineral apatite. And the reason I'm highlighting this is because we have now started working on Melty inclusions in lunar basalts, which we think are actually great candidate to tell us about a part of the lunar history that we can't really be confident about by just looking at apatite. Okay? So, question is, why Melty inclusions? Well, the apatite is a great mineral, and I think it has been great to work on apatite and to lead this field over the past 10 years, but I think we have collected enough data to see where the gaps are and actually what processes we might be able to address using apatite and what we can't, right? The important thing to realize is that apatite forms at very late in the crystallization history of the lunar magma. So there is a lot of potential for that magma to have changed its original signature by the time apatite crystallizes. Okay? I say there is a potential to change. I'm not saying that in every case it changes, but the question is there something else that you can combine with to actually consolidate your story? And that's where Melty inclusions come in, because they form very early, they get trapped right at the beginning of the magma crystallization, and if you are really trying to look for hydrogen and chlorine signature of the lunar interior, Melty inclusions are our best bet. And you might ask, then why didn't we work on those? Well, first of all, Melty inclusions are quite rare, relatively rare in Apollo samples, and secondly, they contain a lot less water and chlorine than the apatite does. 2-3 orders of magnitude less. It is not easy. And as Jack said in his talk this morning, none of this would have been possible without the technological advancements that we have seen in the last 30, 40 years, okay? So let me share some of the results with you, and mind you, a couple of samples at the top have just arrived literally in the last hour, right? So you will excuse the incompleteness that might have in the data. But on the right, you see some pictures of Melty inclusions in some of the Apollo samples. They are crystallized. That actually introduces another layer of complexity in interpreting the data, but we have ways of actually surmounting those issues. We selected a suite of lunar basalts. Some of those have been looked at by other investigators for just maybe water abundance, but not for hydrogen isotope composition. And nobody until now had actually looked at the chlorine signature of lunar Melty inclusion. So the paper that was accepted this week is the very first paper reporting chlorine isotopes in lunar Melty inclusions from mare basalts. So just to give you a couple of examples, when we looked at the water signatures in the 2 Apollo 11 samples, we see that actually Melty inclusions are not as pristine as we had hoped, right? And this is simply a reflection of how complicated it is to actually unravel the volatile history of lunar samples. And remember that these samples were not collected because they had Melty inclusions originally. So we are trying to get best out of them that we can in the laboratory. And the two things that you see is that in the Melty inclusions, there are still signatures that they suffered effects of diffusive loss of hydrogen and perhaps an element of solar wind mixing. So there is a lot of teasing out to be done. But we believe that we can actually tease these things out, and when we compile the entire data set, they look consistent with a water abundance in the magma around 250 ppm, which translates to about 25 ppm in the lunar mantle, at delta D of around 0 plus or minus 100 per mil. I don't have time to go into detail into this, but when the paper comes out, you will be able to judge it for yourself. Moving on quickly to chlorine. So chlorine has been probably the most surprising element in lunar rocks, notwithstanding the presence of hydrogen. But the fact is that chlorine isotope signatures in lunar rocks are just very different to anything that we see elsewhere in the solar system. And the question has been, why is that the case? So the first hypothesis was that it is because there was no water in the moon, and that is why the chlorine isotopes behave the way they behave. But now I just showed you that actually that is not the case. There is water in lunar rocks, so that cannot be the only explanation or the explanation. There are other things that have been proposed, including some from our work, where we see some sort of correlation with chlorine isotopes, and these are all apatite data, by the way. Chlorine isotope composition of apatite with the amount of creep that we think that rock has. So we propose that perhaps it is related to the creep formation. So what does the Melty Inclusions tell us, right? Now, when we look at the Melty Inclusions, so here are some of the data. We use our nanosims at the Open University to do that. And what the top line figure is that the chlorine isotopes of these Melty Inclusions are also elevated, around 12 plus or minus 2 per mil. So that's not zero. It's not same as Earth. So the first conclusion that you can draw is that chlorine isotope signatures of lunar magmas were elevated to begin with, right? So it has to be there. It is not because of magmatic degassing on the surface of the moon. It has to start from the interior. Now, whether that happened in relation to the creep or not remains to be seen. Now, what we don't see, and probably you can't see it very well, there is a kind of a flat line there that actually shows that Melty inclusion data don't quite follow the creep mixing line, right? So that means that we are again looking at a number of processes that are actually affecting or giving rise to chlorine isotope signatures once it is erupting. And that is probably what apatite is recording, whereas Melty inclusion is simply recording what is there in the lunar interior. So if I may conclude, we think that the lunar interior has got about 25 ppm water. Its hydrogen isotopic composition is broadly chondritic, similar to that of the Earth. The chlorine isotope signatures that we are seeing from the Melty inclusions are still elevated. That tells us that the moon has an elevated signature for chlorine isotopes to begin with. And there has to be other processes that we need to investigate and perhaps look at newer samples. And all of these things are viewed from Apollo samples, remember. And that is why there is such a strong case to actually go to the moon and sample other areas that were not sampled by the Apollo missions. So let me just finish by acknowledging our funding bodies, the NASA CAPTEM, without which none of this would have been possible. And of course, my mentor, Professor Larry Taylor, who actually brought me into this field almost 17 years ago. And without Larry, I wouldn't be here. So may his soul rest in peace. So thank you. Everybody's ready to go to the Hornet.
Okay, well,
3, 2, 1.